Hey class. So this is chapter 3, stoichiometry. Stoichiometry is calculations with chemical formulas and equations. So it's like the math portion of chemistry. So let's get started. So law of conservation, as it turns out, there's a law that says whatever we start with in a chemical reaction, the mass does not change when we end the chemical reaction. So the mass of the reactants before the reaction happens and the mass of the products after the reaction happens must equal the same because nothing is created or destroyed. And this was Antoine Lavoisier at the end of the 18th century. So it seems odd to think that possibly the log that you're burning in a fireplace ends up having the same mass as like the log and the oxygen added together equals the ash and all the extra gas that was given off. And we often think that that's just not true, but it fortunately is true. So concise representation of chemical equations, and instead of drawing stuff out like using the models they do for the actual chemical reaction, we tend to make it easier for ourselves and use chemical equations. And here's what the chemical equations look like. Obviously, the hydrogen is the white, and the black ball in the center is the carbon. So CH4, and that's in a gas, and two O2 molecules in a gas combine to form CO2 plus two H2O molecules. Now you will notice that we have the same number of white balls and red balls and a black ball on either side. So when we add up all of the red balls and get 4, and we take a look over here and we see that we have 2 here and 2 here, we end up with 4. We have 1 black ball, and then we have 1, 2, 3, 4 white balls. So the same number of molecules, or I should say atoms, of each element are on both sides of the equation. That's what the law of conservation is referring to. You must have what you start with must be there at the end. So you cannot create or destroy. You can rearrange, but you can't create or destroy. Let's keep going. So take a look at the two that are on the left-hand side of the arrow. So these are the reactants, okay? They appear on the left-hand side of the equation. The products appear on the right-hand side. So that would be the carbon dioxide and the 2 water molecules. Okay, keep moving. The states of the reactants and products are written in parentheses to the right of each compound. So notice that we have gas, 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 and gas. That's what the G stands for. And we'll go over more of that stuff in the next set of notes. Coefficients are what we put in front. So notice that there are 2 molecules of O2, and that's what that 2 goes to. Now that is different. That is different than the subscript. Notice that the subscript here is 4 for CH4. That means that there are 4 hydrogens bonded to the 1 carbon. Okay, that subscript cannot change, but we can change, according to what we have on the other side, we can change the coefficients in front. And that does not change the ratio of like hydrogen to oxygen for the water molecules or carbon to oxygen for carbon dioxide. So let's keep going. Subscripts and coefficients give different information. Yes, they do. So H2O is 1 molecule of water. That means 2 hydrogens and one oxygen. If I have 2 H2O, that's the next slide. If I have 2 H2O, that means I have 2 molecules of water, and then I multiply. So 2 times 2 gives me 4 hydrogens, and 2 times 1 gives me 2 oxygen atoms. So subscripts tell the number of atoms of each element in a molecule, and coefficients tell the number of molecules. Combination reactions. So here I have a combination reaction is when I take 2 or more things and combine them to get 1 product. So you can see it says 2 or more substances react to form 1 product. So on the right-hand side, there will be no plus signs. I will have just 1 thing as a product, and it will be the combination of the 2. reactants. So here are a couple examples. With N2 plus 3H2 yields 2NH3. This, by the way, we will see many times, and just like H2O has a common name of water, this also has a common name. NH3 is called ammonia. I'm sure you've heard of that before. Okay, this is one of our favorite combination reactions. Oh, by the way, combination reactions are also called synthesis reactions, and that's important because we use different names for the same process. Just some people call them synthesis and some people call them combination. This, getting back to my example, this is magnesium. Magnesium and oxygen, when we combine them, it produces a very high temperature and magnesium oxide, and it produces a lot of light. Here's the magnesium burning to great effect. Moving on. So what other kind of reaction types are there? That was just synthesis, so let's talk about some other ones. Decomposition. Decomposition is like the opposite of synthesis, where I have one substance that breaks down into two or more substances. So now I have one substance on the left-hand side. Notice there are no plus signs on the left-hand side because it's only one substance, so there's nothing to add together. But on the right-hand side, we have more than one thing. So that's what decomposition is, just what it sounds like. When something decomposes, it goes from one thing to many things. And here we have 3 examples of decomposition reactions. This is one of our more common decomposition reactions with potassium chlorate, and it decomposes to potassium chloride and oxygen. Combustion reactions. So combustion reactions are just what they sound like, when something burns, but that something is always going to have carbon and hydrogen, and sometimes carbon, hydrogen, and oxygen all together. So a carbon and hydrogen compound is called a hydrocarbon. Okay, so this is rapid reaction that produces a flame. Most often involved hydrocarbons reacting with oxygen in the air. So you will see something with carbon and hydrogen plus O2, and it always gives the same products. It always gives carbon dioxide and water. And that's how you can truly tell that it's a combustion reaction, because it's O2 yields CO2 plus H2O. Okay, that is a combustion reaction. We usually symbolize that with a CO. And I think that's it for today.